Good evening, everyone. Welcome to the McDonald Observatory live stream. My name is Saul Rivera. I'm the online program coordinator here at the McDonald Observatory, and welcome tonight. I'm really glad you could join us tonight. And I'm joined today by my colleague Jay Pickett, Jay Smickett. So my apologies.
You're good. It's kind of a weird last name. Hi, everyone. My name is Jay Smittick. I am the K-12 Education Program Coordinator here at McDonald Observatory. Thanks for joining us tonight.
Yeah, if this is your first time joining us tonight for any of our live streams, welcome. So glad you can join us for tonight. If you've so the way this program works, the way this program kind of works is we'll be talking tonight about star clusters. So kind of like how they form, some of their properties, their life cycles, and we will have a live moderator in the chat just kind of taking the questions. So do feel free to participate in the chat and ask any questions you may have. Also, this stream will remain on our YouTube channel. Some people are joining us from Facebook and Instagram. I can see some people on the Instagram side. Hi, you're here on my right side. And also, if you're joining in a bit late, it's staying a bit early, this is a family astronomy stream. So more catered to our K-12 audience, but people of all ages are more welcome to join in, ask questions, because hey, we all love learning here. And also, this will remain on our YouTube channel. So if you feel free to rewatch it at any time. You don't have to watch this only once. If you have any questions, drop them in. If any question is going to require more detail or would just be cool to answer on air, our moderator will pass it along to us. And with that, let's kind of dive in. So the McDonald Observatory is part of the research branch of the University of Texas at Austin. And even though we are part of Austin, we are not in Austin. We are very far out in far west Texas, getting to about 450 miles away from Austin. So being in far west Texas, being very much in the middle of nowhere, we can get some very nice dark skies. Being in the middle of nowhere lets us get nice isolated areas, these dark skies. We can do some very nice research. We can see far away galaxies, far away planets, and see some star clusters, which we'll be focusing on today. Not only is this good for research, it's very nice for our views, which we'll be looking at tonight. So we are kind of worried at the start of the night about clouds and such, but actually they've been clearing, so hopefully that continues on through the nights. So for myself, I'm currently inside one of our domes here at our visitor center. So here's a picture of that dome. That's also why I kind of look kind of weird tonight. So I am using right now kind of an infrared camera or near infrared. So that's also why I look really weird. I'm not kind of possessed. I just have with the sliding kind of makes me look really weird. It also makes everything kind of look black and white. Also, with the camera we're using tonight, it's connected to one of our telescopes. So usually during our public programs, we have a eyepiece connected to this telescope. It's pictured here on the screen. And also, you can kind of see it behind me right now. But instead of an eyepiece, we have a camera attached to the telescope. It's taking long exposure images, ranging from about 15 to 30 seconds tonight. And that camera is connected to our computer, which is then going to be broadcasted to you guys. So everyone can take a nice view of our targets tonight. And we're going to get a wide variety of targets. If you want some more details about the telescope setup, it's a 16-inch Ritchie Crichton, and the camera details and such, for all y'all more techie nerds, I'm a nerd myself, but not of the techie kind, they'll be in the description of the video. And as kind of mentioned earlier, tonight we're talking about star clusters. But to kind of lead into that, one of the big questions tonight is, what do you know about stars? Feel free to drop it into the chat. Jay, what do you know about stars?
So there's so many cool things about stars, but I guess my favorite things are just how wide and variety their temperatures can be. Can have really cool stars. You don't want to call them cold. They're still pretty hot. And then really, really hot stars. And this also affects the color that they are. What about you, Sowell? What do you know about stars?
See, the thing I know about stars, they can get really big. Like for our sun, for example, we can fit about 1 million planet Earths into the sun, and then you can. And our sun's considered to be a pretty small star in comparison. It's a very common type of star, but it's a pretty small star. But there are some stars out there where you can fit about 1 million types of those of our sun into those stars, and 1 million types of those stars into other stars. It can keep on going and going and going, just kind of keep on going forever, basically.
Just stacking and stacking stars inside of each other.
Yeah, basically just like a Russian babushka doll. And let's see if anyone in the chat's pushed in some of their own. Let's see. And yeah, everyone feel free, you're free to drop into the chat your own thoughts about stars or what you know about stars.
Anything.
Yeah. Let's see. Well, while y'all are thinking about what you know about stars, well, we're gonna drop in the kind of like a little bit of a curveball for you with our first target of the night, which is actually ready, and the clouds actually cleared up for this one, which I was very surprised about. So for our first target of the night, it's this one. Let's see.
Go.
Bam.
Ooh.
So this guy here is a giant space cloud. And it is. Yeah, I've been wondering if you think of this just looks like a giant cloud. It is. It's a giant space cloud, which is a nebula. Nebulas are giant space cloud. That is the literal definition of a nebula. Nebula is just a giant cloud of gas and dust in space. But what do you think this has to do with stars? So and I see some other people have been dropping in their own comments about stars. So Alexa on Insta says they're made of gas. Yeah, and yeah, stars are made of gas. Actually, we're gonna get some more details about how the gas gets involved in this. And actually, this cloud is made of gas, more specifically, hydrogen gas. This cloud here. And I see some other people kind of chiming in on how this cloud is involved with stars. For JMASC3 on Insta, it's their origin. That's actually correct. So this nebula here, known as Messier 17 or the Swan Nebula, is what we call a star-forming nebula. Astronomers are very literal when it comes to naming things. So usually when that's going on, it's so if you're ever reading something about astronomy and we are reading about the name, usually 90% of the time that's what's usually what's going on. If they're talking about like if it's a red shift, that means the light is shifting towards red. A star-forming nebula, it's a nebula cloud of gas that has to do something with a cloud of gas that can birth new stars. Also, if you don't see a swan in here, don't worry. There's other names for this nebula. Other names for this nebula are the Horseshoe Nebula, the Crab Nebula, the Checkmark Nebula, the Omega Nebula. I actually personally see more a Lobster Nebula. It looks like a lobster that's lost its arm. There are lots of names associated with this one. Now, this nebula as well has some more of the more nitty-gritty details. It's getting to about 5,200 to 6,800 light years away from us. For reference, a light year is about 6 trillion miles. It's about 15 to 20 light years across. And it is, as someone mentioned, actually is giving birth to brand new stars. how it's giving birth to brand new stars, I'm going to leave that to Jay. Yeah.
Thanks, Saul. So I'm so excited it cleared up tonight. That Swan Nebula looks beautiful. I'm going to go ahead and jump to another image. Let me get this real quick. And here we go. So a lot happening. We can't always see that with our telescopes here on Earth, especially our smaller ones, even though the 16 inches is a pretty nice sized telescope. But whenever we go out outside of our atmosphere, like with Hubble and James Webb, we're able to capture a lot of those colors that we typically see. So those colors are really important because they tell us a lot about what's happening in this region. So let's talk about why stars form in this region. So specifically, these areas are called molecular clouds, and they're located throughout all the different types of galaxies. And these molecular clouds are huge, they're super massive. They can be 1,000 to 10 million times more massive than our own sun. So they're really huge areas, and being that massive means they take up a whole lot of space. So a molecular cloud can stretch for hundreds of light years wide, so a diameter of hundreds of light years. And to give you context of just how large a light year is how far light travels in 1 year. And that distance is about 6 trillion miles, which trillion is going to be 12 zeros. So 6 followed by 12 zeros. So 6 trillion times hundreds and hundreds of light years, it's a pretty wide area. And so the reason that stars form in this area is because these molecular clouds, they're not filled with hot gas. They're actually filled with cold gas and dust. And so over time, this gas and dust, it clumps together. It's colliding and clumping together, forming these really dense pockets. So a way to kind of think of it is think of having a Rice Krispie treat. And Rice Krispies, they have a whole lot of air in between them. So if we were to smush and smush and smush Rice Krispie treats together, we would end up forming a pretty dense ball. So we would have a heavier ball. And so just like a Rice Krispie treat, these areas that clump together, they're going to get more and more massive, get more and more density. And so whenever that happens, they also get more gravity. So more mass is going to cause more gravity. And so whenever we have enough mass, these clumps will basically get too massive and they'll collapse under their own gravity. So let's get too heavy that they'll collapse under their own gravity. And so whenever they collapse, they're going to continue to gather more and more molecules until they have an increase in pressure. And so whenever we have an increase in pressure, we also have an increase in temperature. So these pockets are not only getting more massive, but they're getting hotter. And so whenever they get to a certain amount of pressure, they're going to get so hot that they start to basically give off heat. And so they're going to form something called a protostar. Now, a protostar is not quite a star yet. It's kind of basically like a baby star that's not fully formed yet. It's almost fully formed. It's almost out of the womb, but it's not quite there yet. And the reason that it's not quite a star yet is because it does not do the one thing that stars do, which is nuclear fusion. So all of these atoms, and specifically hydrogen, that these clumps are pulling together and colliding together, they're not under enough pressure to fuse together and form hydrogen to helium. So they're going to continue to increase in heat and get hotter and hotter and get more and more material until there is just enough pressure that it's going to squeeze these hydrogen atoms together and it's going to start nuclear fusion. And that's when we get a star. Now, backing up a little bit, whenever these protostars form in this molecular cloud, it's not just one protostar that's forming. Typically, we're going to have at least a few protostars to thousands of protostars forming at the same time. And so we have all these protostars popping up. And then just like that one process, all these different clumps are going to continue increasing in pressure until these protostars form into stars. And so this process of forming a star can take about 1 million years. So I know I just kind of went through it really quickly, but this is a very, very slow process. And so whenever we have batches of protostars turning into groups of stars together, so forming around the same time, they're going to form something called a stellar cluster. And whenever we have molecular clouds full of stellar clusters, they're going to form something called a stellar nursery, because all these stars are baby stars. So just like a nursery, yes, exactly. Just like a nursery holds a whole bunch of babies, a stellar nursery holds a whole bunch of baby stars. So as these stellar nurseries continue to grow and produce more and more stars, they're basically using up all that material over time that is in that molecular cloud. And so some of this material is either going to get used up and create a star, or whenever we have a star forming, there's a lot of energy. So it might cause some of this material to get pushed out. And even more exciting, sometimes these stars form and they're really, really massive and they live for a very short time. And so whenever they die, they explode. And that explosion can also push out material until eventually there's no more material left for more stars to form. And that's when we really get our stellar clusters or our star clusters. And so these nebula, just like our star clusters, can change shape over time. And they might not always look like the Swan Nebula looked. It might look a little different. So let's go ahead and see. Saul, are we ready to see our other looking nebula?
Yeah, so sadly, seems we might be a light cloud in the way there. So sadly, we might not get a view of the Cocoon Nebula, at least a live view. But since we were prepared of clouds possibly being an issue tonight, we do have views from other telescopes. So when we're doing observations in astronomy, clouds are one of the issues with those pesky clouds, at least with ground-based telescopes, which is why we do have space-based telescopes in astronomy. That's one of the advantages here. So here view is the view of the Cocoon Nebula. So one of the cool things you can see here in this telescope view, in this other view of the Cocoon Nebula, so it's actually from a different telescope, not necessarily a space-based one, but from in this more colorful image of the Cocoon Nebula, you can see lots of pinks here. So with the star-forming nebula with the hydrogen going on here, we can give the hydrogen that kind of with being lit up by the stars and such. Inside, you can see that nice pinkish color, which you get from the star-forming nebula, nice pink color. Also, you can see lots of these brand new baby stars being formed inside. The stars in the Cocoon Nebula are pretty nice. The other name for the Cocoon Nebula, as you can see, the more formal name is IC5146. The Cocoon Nebula is a bit closer to us than the Swan Nebula, being about 4,000 light years away. And the stars in this nebula are getting to about 100,000 years old. Now, that sounds like a lot for us. Like, for example, like if you're exploring the jungle and you hear about ruins are 100,000 years old, that's like super old. But by star terms, it isn't a lot. For example, our sun. Our sun is a pretty common type of star. It can live for about 10 billion years. If a star comes by in comparison that's 100,000 years old, it's not that much. They're baby stars. They're little bitty. They're baby stars. So these stars are very young. But as kind of we've been mentioning, these stars are using up gas to be born. In this giant cloud of gas, each of these stars are using up some of the gas as they're in their formation. There's only a certain amount of gas in this cloud. Eventually, you're going to reach a point where there's not going to be any more gas to give birth to any more stars. So you're going to run out of gas. There's the leftover gas going to get blown away. And then you're just going to be left behind with a group of stars or a cluster of stars. Well, in this case, usually what will be left behind is what we call an open cluster of stars, which Jay is going to tell you more about while I hunt for a group of stars. And that's actually going to be a pun, which will be paid off once I find it.
Okay.
Also, we see a friend of ours in the chat, so I'm going to say hi. Hi, Abby. And that's good. Let me go find for that cluster.
Yeah. So as Saul hunts for that, so let's go ahead and talk about open clusters. So open clusters are going to be still a group of stars, but these groups of stars, they're loosely gravitationally bound. So they're relatively close to each other, but there is space in between them. That's why we call them open clusters. And there are, whenever we talk about two different types of star clusters, so we have open and globular, open tend to have less stars than our globular clusters too. So they can contain about tens to thousands of stars. So just a few to thousands of stars, which seem like a lot, but when we talk about globular, you see that there's even more in globular. And because they don't contain as many as globular, they are going to be a little bit smaller. So the diameter of open clusters can be about a few light years to up to about 30 light years in diameter. So honestly, not too big of an area. And the cool thing about open clusters is they're found in irregular and spiral galaxies. So irregular galaxies are galaxies that don't really have quite a specific shape. So we just kind of throw them into their own category. And then spiral galaxies are just like our own galaxy, our Milky Way. So galaxies that have spiral arms. So open star clusters, they have a core, and the core is going to be a central area of the cluster where stars are more densely packed. So kind of a higher concentration of stars in this central mass, and then we're going to have more stars kind of spreading out from this area. The core can be a few light years in diameter, and it has a corona. And you probably have heard of that term before, especially if you have seen a solar eclipse, because the corona is going to be the outer layer of a star. And the corona that's surrounding the core of our open cluster stretches for tens of light years away from that central area. So open clusters, as Saul kind of mentioned, they're typically on the younger side, these stars. They can have a few older stars in there as well. It's not completely uncommon, but typically they are going to definitely be younger than our globulars. So the oldest stars that we might find in open clusters will be less than 1 billion years old. So just wee little babies. So we're going to go ahead and see, let's see if we're ready to see a pretty cool open cluster.
Right, we're almost about ready. Ooh, actually, right on cue. Let's see. Ta-da! So this here is called Messi 11, the wild duck cluster. So hence the hunting pun. Now, I will not be hunting the ducks because actually I really do like ducks. Like a lot of my social media pages, like Instagram and Twitter, are a lot of cute duck videos just because I find them very, very, very cute. The like in like costumes and such, just really love them. But this Messi 11, the wild duck cluster. There's one of those open clusters. The reason it's called the wild duck cluster, you may notice that there are actually some really bright stars in the cluster. Actually, you can see 3 of them. So you can kind of might be able to make out a bit of them. Are you able to see my mouse, Jay? I think you are. Can you kind of see my mouse wiggling around? Let's see.
Yes.
Okay. So where my mouse, you see there's 3 bright stars. So there's 1, 2, and 3 right here. Actually, might tone down the exposure a little bit. You can see they pop out a bit more here. Don't worry, the other bright stars will come on back. So 1, 2, 3. So the idea is that these 3 brighter stars are supposed to be ducks that are flying in formation in a V shape. So those are the ducks that are flying in formation. Turns out, like this bright star here in the middle, not part of the cluster at all. It's a foreground star, or you can like say it's a photobomb star, just a random star that's part of the cluster. All these other bright stars, though, they are part of the cluster. There's about 2,900 stars in the cluster. And they're about 220 million years old, which again sounds like a lot for us, but by star terms, these are basically toddlers. they are super, super young. They're really bitty stars. And it's a really cool thing. And another really cool thing about this cluster, you can actually see with binoculars. If you just have a good pair of binoculars, go out if you have dark enough skies and go out here, like especially out here, like at the McDonald Observatory area, but you don't have to be even super dark skies. But if you're in dark enough skies with a pair of binoculars, see around the Milky Way area, you can actually see this cluster with a good pair of binoculars. It's actually a really nice cluster to see. So again, Messier 11, the wild duck cluster. And now let me go hunt for a different one. Let me see if I can catch a different one.
Nice hunting, Saul.
Thank you.
So while Saul was trying to catch our next one, a few more things about open clusters. So when we talk about open clusters in the Milky Way, so just in our own galaxy, we have found thousands, over 1,000 of these open clusters just in our own Milky Way. But even though astronomers have found more than 1,000 of these open clusters, they believe that there are many, many more that they have not yet spotted, but are definitely out there. So when we talk about where these open clusters are located, and I have a picture of a spiral, just like our Milky Way, they are located in what is called the disk of the Milky Way. So if you look on the image on the right-hand side, you'll see we're kind of looking at the spiral galaxy from the side. So spiral galaxy is the disk, the center part, is actually a lot thinner than people recognize. So one of our colleagues likes to compare it to a thin crust pizza, and he says it's the only correct way to have a pizza. But kind of think of a spiral galaxy as a really thin crust pizza, and then it has a core in the center. So imagine someone's put a big meatball in the center of that thin crust pizza. That would actually be a pretty good representation of what our galaxy actually looks like. So when we talk about where open clusters are located, they're going to be in the disk of that galaxy, so kind of floating around the crust. And our galaxy, it has arms, spiral arms. And so these open clusters, they're not only located inside the arms, but they're also kind of moving around in between the arms too. So it is everywhere floating around the disk and kind of orbiting around the core of our Milky Way. Now, another cool thing that we have found out about open clusters is that they actually have planets. So there have been planets that have been discovered in these open clusters. So planets orbiting around these stars. Currently, we know about 1/3 of the stars in open clusters in the Milky Way have planets orbiting them. So again, about every third star in an open cluster possibly has a planet orbiting it. So that's a lot of exoplanets out there. And we have for sure confirmed, so there are 2 known planetary systems in an open cluster called NGC 6811. Doesn't have a fancy name, just has its catalog name. But this is an open cluster in the constellation Cygnus, which is the Swan. So there's 2 known planetary systems in that one. And then in a cluster called the Beehive cluster in Cancer, it has several exoplanets called hot Jupiters. So hot Jupiters are pretty common when we look at exoplanets, and they're just like their name sounds. They are planets that are about the mass of Jupiter, but their temperature is really, really hot. It can be for several different reasons. But we have found several hot Jupiters just in the Beehive cluster alone. So there's a lot of exoplanets and a lot of open clusters out there in our own galaxy. So let's see if Saul has caught our next open cluster.
I'm almost about there. Need a few more. But while I am getting a position, some little cool facts about this. This cluster is known as IC 4665. And funny you mentioned Beehive, because the other nickname for this cluster is known as the Summer Beehive. Or also, the other fun name, kind of to also keep up a little bug theme apart from Summer Beehive, is that it's known as the the black swallowtail butterfly cluster. So we had the Cocoon Nebula, and now we have the black swallowtail butterfly cluster. So see, we kind of have it in view, and now we're going to wait for the exposure to go up. Let's see. So kind of the way with how some of these cameras work. So basically, when we were looking through the telescope, we are kind of just letting to see how much your eyes kind of got light, but through the camera, you're actually kind of you have like exposure times. You're kind of like putting a timer and choosing how much light you're letting come in through after a certain amount of time. So for this one, we have about 7 seconds coming in. We're going to increase the exposure a little bit more to let a bit more light in. But a cool thing you might be noticing right off the bat is that there's a lot more open space between these stars right off the bat. So that's also why it's actually a bit more zoomed out here, so we can actually get all the stars in view here. And these stars are about 1,100 light years away from us, and they're also a lot younger. While the ducks in the wild duck cluster, but the stars in the wild duck cluster are about 220 million years old. The stars in this cluster are getting to about 55 million years old. They are also actually, we believe there's evidence that they're currently in a collision with an older cluster called Colander 350. So these stars can actually be colliding with other clusters because things in space are moving around. So it's actually kind of cool seeing that these clusters also even come in like different kind of shapes and combinations of sorts. Actually, it's kind of a little pretty, kind of like little stars kind of like stretching across each other. Actually, let me zoom in a bit here so we can kind of fill up the field of view a bit more. Just kind of stretching across here. Ooh, I actually kind of like this view a lot. It's actually really pretty. It's kind of growing on me. But I was saying these clusters come in different shapes and types. So sometimes what can happen is that as these stars are forming in the nebula, in the star-forming nebula, you can have a situation where so many stars can form so close together they become bunched up. They become what we call gravitationally bound. That means their own mutual gravity keeps them from drifting apart. Basically, it's like if people are holding their hands together and trying to run in opposite directions, but in star form. And they become a type of cluster called a globular cluster, which honestly, even though this is really cool, globular clusters are my personal favorite type of cluster because they just look so cool, especially in a telescope. And I'm going to go and switch and look for my favorite type of globular cluster. So yeah, I'm going to go look for that one.
Yeah. So while Solo is doing that, also, I'm not trying to copy Soul, but globulars are also my favorite. But before we moved on from open clusters, I thought it was really cool because I'm going to scroll back. Star Pictures Miami earlier in our stream actually mentioned that M7, which is Ptolemy's cluster, was their favorite open cluster. So I thought it'd be really cool to share it before we moved on away from open clusters. But let's go ahead and move on to globular clusters, which, as Sol said, are the best type of clusters. No preference whatsoever here. So globular clusters, just like open clusters, they are gravitationally bound. But unlike open clusters, their gravitational boundness is going to be even stronger because we have more and more stars. So it's going to be a lot denser. And another difference between open and globular is that open, since they are younger, these stars tend to be more violent and energetic, and globular, they tend to be a lot older, so they're actually more stable stars. And since they are so dense, there's going to be tens of thousands to even millions of stars in these clusters. So there is a lot of stars we're talking about here. And another difference is that these stars, or these star clusters, are found in all the different types of galaxies out there. So not just irregular and spiral, but also that third type, which is elliptical. But they're not just found in all different types. They tend to be found in galaxies that are larger. And I'll talk more about that in a second. So these stars, as I said, they tend to be older and redder. And astronomers believe that these stars in these clusters might have even formed shortly after the Big Bang. Now, I said that these stars tend to be redder, but if you're looking at the pictures on your screen, you're probably seeing some blue stars in there, and your eyes are not lying to you. So we do notice that there are some blue stars, and they tend to be large and very, very bright. And what we know about stars and their life cycles is that typically, if a star is big, blue, and bright, they tend to be younger. But the stars in these globular clusters that are big, blue, and bright, that's not quite the case. We believe that these stars form whenever we have stars that basically collide and combine and form bigger and brighter and hotter stars. So we think that these stars are blue not because they are young, but because they're just so much hotter and so much brighter. Now, these stars, since there are so many of them in these clusters, they're definitely going to take up a lot more space in the galaxy. So diameter-wise, they can range between 50 to 450 light years in diameter. So they are massive and huge and take up a whole lot of space. And their intense gravitational attraction, so that attraction between them, gives the globular stars their regular spherical shape. So Saul and I like to call them globular, but some people like to call them globular. It just feels weird to say globular. I like globular better. But they are also called globular because they do have that spherical shape. So we tend to find our globular clusters in the halo of our galaxy. So remember we talked about the disk, so that thin crust pizza. So the halo is going to be the area around the top and the bottom. So the area that surrounds our disk. And so our globular clusters kind of float around in that area and stay on the outskirts of our galaxy. And there is a lot less of these globular, or a lot less of these types of clusters. There's actually less than 200 clusters that are known in our Milky Way. So that's a lot less compared to the thousands of open clusters that are out there. And so they tend to be found in the halo. We can find them in other areas, but they tend to hang out in that area. And then most of the globular clusters in the Milky Way, we're not quite sure as astronomers where they exactly formed. We do know they formed differently, but one of the theories, and it's kind of cool, that they think globular clusters came to be is something called galactic cannibalism. So whenever we have a larger galaxy, like a large Milky Way, kind of on a collision course with a smaller dwarf galaxy, and it's going to basically rip apart that galaxy and kind of merge it with our own. And they believe that the globular stars might have formed that way. So kind of cool when you think about it that way. So, Saul, are you ready to see a globular cluster?
We are. All right. So here we got Messier 13, known as the Great Hercules Cluster.
Ooh.
Yes, so pretty. So actually, now I'm doing introduction. Actually, a question that came in from Instagram from Taurus Flores and Alista, who names the clusters. So actually, you might have heard us give like some of the clusters different names and the nebulae and such. So the names actually, so there's kind of like a catalog name. For example, you hear like for this one example, M13. So a lot of the way astronomers did research back then is they would point a telescope in direction, look through the entire night, and write down whatever they saw. So like a weird fuzzy star, for example. For example, M13 looked like a weird fuzzy star in those telescopes. If the weird fuzzy star moved over many nights, congrats, you found a comet. If the weird fuzzy star didn't move, find a larger telescope because you got no idea what you're looking at. There is a French astronomer called Charles Messier who really wanted to find comets. Each time he found a comet, that, or Barry each time found a fuzzy star that wasn't a comet, he'd add to a list. Barry at a not a comet, don't look again list. This is number 13 of that list. Barry is not a comet, don't look again list. So that's kind of like some of the catalog names. Sometimes the catalogs come from like, for the Messier ones were of that list. Others like NGC, the new general catalog, so on and so forth. When they get other names such as like, for example, Great Hercules Cluster. So the constellation is actually in the constellation of Hercules. So it's kind of like where its appendix would be. At least I think that's where the appendix would be. My degrees in astronomy, not anatomy. That's just for the general area of where I would believe his appendix would be. There sometimes like with the swan, so you're like, hey, it kind of looks like a swan. So that's where it comes from. Sometimes the names can be of whoever found it. So, for example, Jay mentioned Messier 7 Ptolemy's cluster. Kind of looks like Ptolemy. Well, doesn't look like Ptolemy. Ptolemy was the one that discovered it. If it looked like Ptolemy, well, there people look very different in the past. That's kind of like where some of the namings come from. Also, for another one from Alexon Instar, these actual life images, these are. So each time one of these popped up, I have like a little life image in the bottom left corner. They're actually what the telescope is seeing right now. So we by chance see like a little streak coming in through like this image is usually a satellite that has come through. We haven't really had any of these in the stream so far, but they do pop up in our stream sometimes. Actually, during one of our dark sky streams in April, we actually did try purposely seeing if we could see in the part of the sky when we get a satellite trail coming through to see, kind of talk about satellites and light pollution. But anyway, kind of going back to this cool guy, Messier 13, this cluster we're seeing here is literally hundreds of thousands of stars. The estimates go from 300,000 up to 1 million stars. You're seeing almost, but you might be seeing almost 1 million stars here. These stars have been stuck this way for almost their entire lives, 12 to 13 billion years. And remember, our current estimate for the age of the universe is 13.8 billion years. These have been stuck this way for a long time. And remember, these stars aren't stuck together. They are still individually moving. They're moving around a center of gravity here. And these individual stars are moving. There is a center of mass here, and they're so cool to actually just see through a telescope as well. Some descriptions are they look like shattered diamond on black velvet, or a firework, or a kaleidoscope, or shattered glass, or some say it looks almost like a spider web with dew on it. It's so cool. It's one of my favorites. As Jay is mentioning, these stars can sometimes just individually collide with each other and become these bluer stars, these blue stragglers, as we call them. And when stars get more massive, they actually are fusing material at the core a lot more quickly, which is going to speed up their fusion process and going to make them reach the end of their life a lot more quickly. But no matter what's going to happen if they are fusing material more quickly, if they're more massive, or they're very low mass star, a star is going to reach the end of their life at some point. Depending how massive the star is when it reaches the end of their life, it's going to change that ending event. Most stars, when they reach the end of their life, are going to reach what we call a planetary nebula. Nothing to do with planets, by the way. It's one of the cases where astronomers called something for so long that by the time we found out what it actually was, the name stuck. But it's still a really cool thing to kind of see. And I'm going to try to find one of these. And Jay's going to tell you a bit more about them, because they actually are really cool events.
Thanks. So yeah, and I have a couple of clips to show y'all too. So with a planetary nebula, that is something that's going to happen to a low mass star like our sun. So when we look at and compare the different stars that we know of in the universe, there's going to be stars that are really, really massive and stars that are really, really, really low mass. And our sun falls somewhere around the middle, actually right below average. So this the stars, like our sun, throughout its entire life, it is converting hydrogen into helium. So hydrogen is the fuel that keeps it going for most of its life. And currently, our sun has used almost half of its hydrogen up. So our star is about 4.5 billion years old, and it's going to live for another roughly 5 more billion years. So at the end of that extra 5 billion years, it's going to completely run out of hydrogen. And so whenever it runs out of hydrogen, it's going to form something called a red giant. So whenever the star runs out of hydrogen, it's going to start expanding because the core is collapsing. So this expansion is going to take about 1 billion years, and it's going to grow 100 times bigger than what it is right now. So I'm going to show it one more time, because as you can see, whenever it's going to grow to a red giant, it's going to swallow up absorb most of the inner planets, including Earth. And so as it's getting bigger and bigger, it's also going to get brighter and brighter. Surprisingly, though, it will not be getting hotter. So remember, stars, they have different colors. And so whenever we have a star that's more reddish or orangish, they're actually going to be a cooler type of star. And then our bluer stars are going to be our hotter, blue-white are going to be our hotter types of stars. So once it has reached the limit and become a red giant, it's going to basically start fusing that hydrogen or helium that is created throughout its life into a heavier element, which is going to be carbon. And so it will fuse carbon for a few million years. And then once it has reached its limit of fusing carbon, gravity can't really hold the star together anymore. So it's going to start to shed off all of its layers. So it's going to kind of push off all its layers. And once it has pushed off all its layers, all that will be left over in the center of all of these elements will be the leftover core of our star, which is going to be called a white dwarf. Now, white dwarf stars are not very bright, but they are very, very, very hot, and they're very dense. So the core of our sun will be about the size of the Earth once it has shed off all of its layers. But remember, I said it's really, really dense. So if we were going to take, let's say, a sugar cube amount of material from this white dwarf star, that sugar cube of material would weigh as much as a car. So there's a lot being compacted in this one little area. And so once that white dwarf star has formed, it's still going to live for a long time, because all that's left for it to do is to basically cool off. But this white dwarf star is very, very hot. So the surface of the star can be about 180,000 degrees Fahrenheit. And to give you a comparison, the current surface temperature of our star is about 10,000 degrees Fahrenheit. So it has a lot of heat to kind of cool off. And so this cooling off of heat will take several billion more years until it eventually has completely cooled off, and it's going to theoretically form something called a black dwarf, which is just basically complete leftovers of our star. And I say theoretically because technically the universe, we haven't found anything that old yet. So we don't know for sure, but still those extra layers that it shed off creates a beautiful cloud called a planetary nebula. And since that white dwarf star is so hot, it's going to energize the atoms in this nebula, and it's going to cause them to glow. And this cloud of gas and dust, it will continue to kind of disperse out for about 1 million years or so until it completely fades. So these planetary nebula will last for a good while, and they're really gorgeous to look at. So are we ready to look at the one for tonight, Saul?
We are. So the nebula we have for tonight is a kind of famous one known as Messier 57, the Ring Nebula.
Ooh. Looks really
good. It's actually really vibrant tonight. So you can probably guess why it's called the Ring Nebula. It's one of those that, hey, looks very much like a ring. Other names nicknames we have here for the observatory are the Cosmic Cheerio, the Giant Space Donut, the Eldritch Onion Ring, depends how hungry you are. And when you see it here through a telescope with naked eye, a lot of people see a very vibrant blue color. Some sites might see it more gray. A lot of it depends on your eye. But here you can see it kind of looks like a nice little smoke ring. So as kind of John was mentioning, those hourglass got pushed away. The also really cool thing is the angle we're seeing it at. So you can actually get a nice 3D shape of it. It'd be the shape of American football. Just we're seeing it kind of like edge on, like the points kind of coming towards you almost. Also the cool thing you can see here that you can't really see through an eyepiece, at least with a telescope like the one we have here, is the white dot in the middle. So the white dot we can see kind of over here is the white dwarf star, that leftover core. So we're seeing the layers getting pushed away here. And this nebula is still growing. So kind of since releasing friction in space, that's still growing. And it's growing at a rate of about 15 miles a second. As it's growing, it's kind of fading away with time. That's getting further and further away from the core. And it's actually just a really pretty object to look at, both with the telescopes and with the cameras in here. And it's just very vibrant. Also, a really cool thing that I saw when I was playing is we actually kind of got a little bonus object here, very, very far away. So as kind of Jay was mentioning earlier on with the star clusters and such, with the globular clusters we have kind of above the disk of the galaxy, and with the open clusters are kind of being formed in the spiral arms, we can actually see some spiral arms here. If you see in the background, you can see there's a background galaxy here, really, really far away galaxy, and you can actually make out some nice spiral arms to this background galaxy. So we got a little bonus galaxy here tonight, just in the background. So make sure to wave. It may take several millions of years for them to see that wave, but it's always polite to give little waves. Yeah, so we have some nice targets here tonight.
Mm-hmm.
Now there's another, so the Ring Nebula itself is getting to about 2,500 light years away from us. And it's about a light year across, at least this nice thick ring part of it, and can actually extend a lot further when seen through the infrared. And there's been some nice pictures taken of it through kind of like some telescopes, like with like James Webb and such, for example. And we can get, again, there's some really cool pictures of it. But kind of there's another target that I kind of want to show you, not through this telescope, but just because it's too small to be seen. But there's actually a picture taken by Hubble of a different thing known as, and I gotta pull up the name just because it's one of those with a bit of more numerical number, known as NGC 7027, or the Jewel Bug. As you can see here, looks kind of like a jewel bug. And so you can see this planetary nebula has a bit of a cooler shape to it. It's about 3,000 light years away, so not that much further away than Ring Nebula, but it's a bit small. While the Ring Nebula here, the very vibrant part, is about a light year across, Jewel Bug is about 0.1 light years. We're kind of still giving a bit of that bug motif going on, but also it's so small. We think this star died about 600 years ago. So by star terms, it just died. Actually, the Hubble Space Telescope thought before they pointed the Hubble Space Telescope at this nebula pictured here, they thought it was a protoplanetary nebula. Like they thought this nebula was giving birth to a new solar system, being the end of one. Like we're still learning more about these, and they're still being formed even recently. Like there's so much cool stuff going on, and so many cool shapes and colors, and it's lots of vibrant stuff going on in space. Mostly when stars die, this is the kind of stuff they can leave behind. But if a star's a lot more massive, like let's say it's getting to about 8.5 times more massive than the sun, they can go off with a bang. You can probably get an idea of what kind of bang we're talking about. But in case you want to get more details about the type of bang, I'm going to hand it back off to Jay.
Thanks. So yes, as Saul said, whenever we have stars that have a higher mass, a much, much higher mass, at least 8 times more massive than a star like our sun, that's whenever we're going to have that really exciting supernova. So let's see, like bang. Okay. So the reason that we have a supernova with these type of stars, you wouldn't really be able to tell from the beginning of their life, because the beginning of their life, they actually kind of have a life cycle similar to like a low mass star like our sun. However, they're going to be a lot bigger. So they're going to run through that hydrogen fuel a lot quicker. So kind of compare it to 2 cars on a highway. Let's say we have a Prius versus an 18-wheeler. They might be going the same distance, but that 18-wheeler is going to burn through their fuel a lot quicker than that Prius because they have a lot more mass to tow with them. So same thing with our high mass stars. They're going to burn through that hydrogen fuel so much quicker because they are getting so hot and so bright. So once they have used their fuel, they're going to swell just like our red giants, but this time they're going to be a lot bigger because they're making even bigger and heavier elements. So low mass stars, they're going to create helium and carbon, but high mass stars, they're going to create heavier elements like neon, oxygen, and then ultimately iron. So whenever they fuse to create their heavier elements, the iron cannot fuse anymore. So whenever they have that iron core, it's going to collapse, but the collapse happens with so much energy that it's going to create an explosion. So the supernovas are actually pretty rare in our Milky Way. We typically see about one every 50 years or so. But it's pretty exciting because we just learned about this, I think it was last week, that there was actually a supernova that they just found in a distant galaxy. So if you notice in this picture, it's kind of pointing to it, but in the center of a spiral galaxy, we have something called a core. And in this picture, you can kind of see a bright object. Actually, looks like it's even brighter than the core of this galaxy. And that is actually a supernova. And they just discovered this year in July. So little under a month ago, actually. I think it was July 22nd. So this was discovered in the galaxy NGC 7331. Not a fancy name for it, just got its catalog name. But this galaxy is about 45 million light years away from us. So really cool, kind of bring current news into it. I thought that was exciting. But whenever this explosion happens, it's going to send out a massive and hot shock wave from the star surface, and it can cause a very, very bright, basically events in our night sky. And so depending on how close and how massive this star is, we can actually see this for at least a week. But if we have stars that are really, really massive, like the star Betelgeuse, maybe you've heard that name. Maybe I shouldn't say it 2 more times. But whenever Betelgeuse is going to go supernova, we could possibly see that in our nighttime sky for up to several months. So supernovas are very exciting, but they're also really, really important. But one more thing about seeing them in our night sky is that we actually know that ancient civilizations actually witnessed these supernova that happened several hundred years ago. So there was a term that used to be in astronomy called guest stars, and that term actually originated from a Chinese astronomy term. And so they were marking down these guest stars, the stars that would be really, really bright and then kind of disappear. And now we know from looking back and looking at records that these civilizations were actually witnessing supernova in their nighttime sky. So pretty exciting. But as I mentioned, supernova and these type of nebula called supernova remnants are really, really important because whenever this explosion happens, it's going to push out all those heavy elements that the star created and also even created in its supernova explosion. And those heavy elements are actually the essential ingredients for creating objects like planets and objects specifically like Earth. So without these supernova and these supernova remnants, we actually would not even be here right now. So maybe you've heard of the phrase saying that we are all made of star stuff. that is literally where this comes from. So we really owe it to our supernova and our supernova remnant. So let's see. How are we doing? So I know this one's going to be a little fainter.
Let's see, Nita. Still about a minute or so more, but it's actually is visible. So it's on a good track.
Cool. So one more thing about these massive stars is that whenever they go into the explosion, they will have something left over other than the remnants. So depending on the mass of the star, we can have something called a neutron star. And these neutron stars are really, really exciting things happening out in space. They are basically a sphere full of neutrons. So the neutrons of an atom, there's a whole sphere of them, and they are constantly spinning. They spin about once every several seconds. So they are moving very, very fast. And then if we have a very massive star, whenever we have that collapse, basically no part of the core will survive. And that's when we are left with a black hole. So pretty cool with our massive stars. We do have a question in regards to our ring. So I'm going to throw it over to you. Let's see. Do the number of rings provide any scientific value?
All right. Thank you, Jay. Mm-hmm. Yeah. So question from Charlie. So do the number of rings provide any scientific value? Kind of interpreting for like things like the Radiant Nebula or such. So so from our host said, so they represent the number of pulsations from the host star releasing gas clouds into space near the end of its life. So as the host star, so the central star is kind of done, it's kind of like pulsating. So that's mostly what it can represent. So, but that's mostly what's going on there. So kind of like it's pulsating kind of near the end of its life. That can give ideas. So something, for example, for the jewel bug, kind of like with the way that pulsation's going, could give us actually an idea of, hey, there might be a binary system in there based on the pulsations. Like, hey, is it like a nice even kind of ring happening, or does it seem like there might have been the kind of actually, if we can pull up the picture of the jewel bug, we can actually see that kind of going. Here we go. There we go. So you can see there's kind of seems to be like going from along the top and along the bottom. So actually, due to that shape there, some scientists think that there might actually be a binary system at the center. So that's one of the little hints. They still need to get more data, but that's actually one of the thoughts they have on that. Yeah. And actually, our target is ready. So we're going to go with the last thing, NGC 6992, the Eastern Veil Nebula.
Ooh.
So this object is huge in the night sky. Reason it's called Eastern Veil Nebula is we can't fit the full Veil Nebula in the telescope. To give an idea of how big the Veil Nebula is the Veil Nebula was the size of the full moon, it would be about 6 full moons across in the night sky. This thing is huge. And it is one of the a supernova remnant. As you can see, some people say looks kind of like, you can see why it looks like it's called veil. It looks like almost like a wedding veil. I just think it's like sitting on water, kind of like a river flow. Some say it looks kind of like pieces of like kind of like neurons of a brain. I heard someone say it looks kind of like the webs of a black widow, like a jellyfish. For me, kind of like for those that play lots of Mario Kart, this is what Rainbow Road would look like if it was real. And this is just so cool. Like it's an actual like leftover remains of a star. Like they think the star that created this was about 20 times more massive than our sun and exploded about 10,000 to 20,000 years ago. And it's huge. Like it expands the sky. It's so cool. Yeah. We've been actually able to fit a good number of stuff tonight.
Yeah, I'm grateful the weather worked out for us.
Yeah. Oh, from Alexa and Itza. So about this picture of the Veil Nebula. So this one is not 6 full moons long. So the full Veil Nebula, like the full object, is about 6 full moons across the night sky. This thing specifically is pretty small. Uh, so I'm so for this thing will only be like a very small section. So with this telescope, we're usually pointing at the moon. We'll only get about like you can see like an eighth of the moon's disk. But like basically for this, imagine this about the length of 6 full moons across in the night sky.
So left to right, how many light years? Question from Brian.
Let's see. So from left to right, it's getting to about 65 light years.
Ooh.
Oh, Olive, will a scope like the Vera Rubin be able to image the complete Veil Nebula? So from my understanding of the Vera Rubin, I believe it will, just from the capacity of like how that thing's been able to get galaxies and such, and with the amount of like air in the sky, it would. If it will be used to, if the type of research it will be doing for Bell or Veil? Oh, Veil, like a wedding veil, like Veil, that kind of stuff. And for location of the Veil Nebula, it kind of goes near the constellation of Cygnus Swan. Oh, and kind of going back to Vera Rubin, for the research you'll be doing, not sure if it will be imaging this nebula, but I believe it would have that capability. But yeah, I think it will. Like that, the Vera Rubin telescope is awesome in its capabilities. Yeah. So let's see if we have any more questions coming in. Now is the time to ask any extra questions. Let's see.
So we have one from YouTube in terms, I believe it's going back to the ring. Is it called outgassing? Whenever it's being pushed out.
Let's see. So will admit I do not remember that one. I will have to read up on that. Yeah. Oh, and I see a question came in from Ramiro Gonzalez. When was the Veil Nebula first observed? It was first observed in 1784 by William Herschel. See, lots of good questions tonight.
Yeah.
All right. I believe that's about all the time we have tonight. Thank y'all so much for joining in. If you've arrived late or want to rewatch the stream is remaining on our YouTube channel, McDonald Observatory on YouTube. We also have streams of many other kinds from the sun to galaxies, from the control room of the Hobby Airworthy Telescope to books we recommend to like lots of other types. We've done almost 80 of these so far, so feel free to pick and choose the ones you like. Feel free to like, comment, interact. It does help the algorithm and just kind of keeping these streams going. And we really hope y'all enjoyed. Also, the Visitor Center is open to the public year round. We do public star parties Tuesday, Friday, and Saturday. usually, except if holidays kind of can mess with that, but usually Tuesday, Friday, and Saturday. And we're open year round about Tuesday through Saturday. If you visit, we do recommend making reservations just for to ensure they can attend our programs. We do programs during the day and night, and hopefully you can visit. We get about over 80,000 visitors from all around the world throughout the year. And hey, you might even get JRI as one of your tour guides if depending on when you visit. Yeah, hopefully you enjoyed and catch one of our other streams. And so yeah, like, comment, share the stream as well. And yeah, keep science education going.
Yeah.
Yeah. Y'all have a good night.
Hi.